Okay, the recording and the microphone are active, so let us go to our lecture. And the first, I will keep you going with the same method of the previous lecture. Please tell me whether it is good or not, if you prefer that I write by hand and so on. This is a sort of mixed method. So we introduced the idea of curl. Curl of a vector is this guy here. It's defined as nabla times f, and times in the sense of the cross product, so you can compute it by a determinant, and this is the expression of the curl of a vector field f. So if you are able to keep this expression in your mind, so to know it by heart, this can be useful, okay? And curl is very useful. The physical meaning is quite transparent. The curl measures the vorticity, or if you want, the quantity of rotation of a fluid having f as a velocity field. Okay, if you think of a fluid, for instance, the air or the sea, the ocean, and at any point the particle of the fluid have a velocity, and so the velocity field of the particle of the fluid have a rotation, a curl which is non-zero whether there is a rotation. You can clarify this idea. I just give you some hint. I don't want to develop it because we don't have time, even though it is interesting and gives you some intuition of what we are doing. So if you compute the curl of the velocity field of a rigid body, so any point in a rigid body, for instance with a fixed axis, has a velocity, and so on the rigid body you have a velocity field. You compute the curl of that, and this is proportional to the angular velocity of the rigid body. It is constant at any point and is proportional to the angular velocity. This means exactly that the curl measures, so to say, in quotation mark, the quantity of velocity, the quantity of rotation that your field has. Okay? And what we found is that a conservative field is irrotational. So as curl equal to 0, which means that a conservative field has no rotation in itself. This is the qualitative idea. Okay? Why the conservative field has no rotation? Mathematically, it is easily said. Since a conservative field admits a potential through Schwarz's theorem, what you find is that all components of the curl are equal to 0. So mathematically, it is very easy. From another point of view, the idea that we will try to develop now is that when you have some rotation in your field, then following the rotation, you can construct the circuits, the closed curve, on which the line integral of the field is not 0. So the field is not conservative. This is the idea, but we will develop it a bit more today. Okay? And so what we found is that a conservative field is always irrotational. So as a consequence, if a field is not irrotational, then it is not conservative. So in principle, what you have to keep in mind is here is f is conservative, then the curl is equal to 0. This is logically equivalent to say that whenever the curl is not 0, then f is not conservative. Notice that when I say curl of f equal to 0, I mean identical equal to 0 at every point. If there is only one isolated point in which the curl of f is 0, this does not count. I'm saying identically 0. Okay? And vice versa, if the curl of f is not identically 0, then f cannot be conservative. This is the very important fact I want to stress. But now I give you an important example. The important example is the following. You have this field. This is a very, very famous field, which is made like that. Okay, I give you a three-dimensional version, but of course, what is important here are just the two first components. So it is a good example as a planar field. However, for coherence with the rest of the lecture, let me give you the three-dimensional version. You have an x component which is minus y divided x squared plus y squared. A y component which is x divided x squared plus y squared, 0. So first, let me remark just a remark that omega, I call omega the domain of f, so the set of the point of R3 in which the expression that define f, the expressions that define f are well defined. So we just have to avoid that this denominator goes to 0. So we have that omega is made of all points of R3 except the z-axis, where both x and y are equal to 0. Okay? Of course, if you refer to the two-dimensional version, where only the two first components are there, the domain is R2 minus 0. So very often in books you find this version. First, you have that f is irrotational. You have to compute the curl of f. So let me write down again what is the curl of a vector field f. These are the three components. The first component, the x component, is dy f3 minus dz f2. Now f3 is equal to 0. The third component is equal to 0. In f2 there is no z, because f2 is this guy here. Since in f2 there is no z, also this is equal to 0, and all this component is 0. The second component, so to say the y component, dz f1 minus dx f3, this turns out to be 0, 2, in a perfect analogy with the previous one, for the same reasons. It remains the third component of the curl of f. So let us write down this computation, this component, and we have dx f2 minus dy f1. Here we just recall the expression of f2. Here it is, and the expression of f1. Here it is. So when we differentiate, first we differentiate x, we obtain 1, and then we multiply by the denominator, so we got here x squared plus y squared. Minus, we differentiate the denominator, we got 2x to be multiplied by x, so we have 2x squared. Okay? So we put terms in order and we get y squared minus x squared. Analogously, what we get from here, from the second term, is x squared minus y squared. And so it is clear that everything cancels. And this is equal to 0. So this field is irrotational. Okay? But the other thing to be made here, to be understood, is that but f is not conservative. Okay. In order to do that, we exhibit a circuit on which, so the line integral, so the circulation of f is not 0. And so this circuit is very simple because it is just any circle centered at the origin, irrespective of the radius. So irrespectively of the radius, we have, so let me see whether I'm able to do that. Okay, wonderful. Let me center a bit better. No. Okay, leave it like that. Hey, this is a circuit, and we can define gamma as r of t given by cosine of t, or if you want, capital R cosine of t, which is the x component, r, capital R, sine of t, and then 0. Remember that in all these examples is totally irrelevant. So this is a circle which is run through with a uniform velocity. This is the uniform circular motion with angular velocity 1, if you are interested to this. And r dot is equal to minus r sine of t, r cosine of t, 0. And then we have to write the field. Okay, let me copy the expression of the field here. So we put it here. So this is f, and this is equal to minus r cosine of t, and here you have r square cos square of t plus r square sine square of t, and here r cosine of t, r square cos square of t plus r square sine square of t, 0. And so notice that every denominator here is simply r squared, because cos square plus sine square is equal to 1. So this is r squared 2. And so you got here 1 over r minus, sorry, here it is a mistake, this is sine of t, minus sine of t cosine of t. So now if you want to compute the circulation of air or f on this circle, sorry, here there is a 0, we have to write down f of r of t times r dot of t dt, and of course from 0 and 2 pi, and here you have integral from 0 and 2 pi 1 over r minus sine t cosine T0, this is F, dot